trying to get a handle on how AI really understands images and text together, right down to the individual pixels. It can feel, well, honestly, a bit overwhelming. Lots of jargon, complex systems.
Oh, absolutely. It's a complicated space. The standard way of doing things for these pixel-grounded multimodal large language models, MLMs, it often looks like building this intricate machine, right? Separate parts for seeing, for segmenting, for language.
Right, like an assembly line. But today we're diving into something that kind of pushes back against that. You, our listener, actually sent over a paper and notes on pixel sale. And what jumped out at me was, well, how straightforward it seemed, relatively speaking, for such a complex task.
Exactly. Pixel sale is really a departure. It's asking fundamentally, can we get this top tier pixel level understanding, but with a much simpler architecture?
Okay, so the problem with the existing models, the established ones, is this reliance on all these different bits and pieces, vision encoders, segmentation specialists, that kind of thing.
That's the core challenge, yeah. The researchers call it high system complexity. Think about a typical setup. You've probably got a clip encoder, maybe for the high-level vision stuff.
Hmm.
Then for the pixel details, you bulk on something like SAM, segment anything, or maybe mass 2 former. You see this in models like Lisa, Glam, OMG
SAT2 VA2, right?
SAT2VA, yeah. And each of those adds complexity, parameters, more potential points of failure or inefficiency. It can limit how you scale the model.
Okay. So Pixel Sale is trying a different path. Less. Less piecemeal. What's the core idea driving this simpler approach?
It draws inspiration from this concept called SAIL, stands for Single Transformer as a Unified Weixian Language Model.
Single transformer.
Yeah, the basic idea is you train just one transformer network to handle both the visual stuff and the text right from the get-go, frankly. So you don't need that separate big vision encoder.
Ah, I see.
And this unified approach has actually shown promise before for image-level tasks like visual question answering, VQA. Models like Solo and EV used something along these lines.
Interesting. So instead of separate eyes and language brain, Pixel Sale is aiming for a much more integrated system within that single transformer.
That's a good way to put it. And what's really novel here from an academic angle is that pixel sale is apparently the first study to explore the simplest encoder-free architecture, specifically for these pixel-wise MLM tasks. They're really probing the minimum complexity needed.
That feels like a pretty bold move, especially given how complex these tasks are. Okay, so we get the why, the push for simplicity. Let's unpack the how. What are the key technical innovations, the really novel parts that let this single transformer do pixel level work?
Right. So pixel sales ability rests on basically three core technical ideas. First up is the learnable upsampling module.
Upsampling. Okay, we hear that term a lot with images. But what's special about their approach here, especially since they don't have those usual segmentation decoders?
Good question. Its main job is to take the low resolution visual tokens that come out of the main transformer and refine them into higher resolution feature maps. You need that detail for pixel tasks.
Because they ditched the complex decoders.
Exactly. So they needed something lightweight but effective to get that spatial detail back. And what's interesting academically is how simple their design is. It's just a transposed 2D convolution, then a depth-wise convolution.
Huh.
They specifically aim to keep it as simple as possible. That's kind of their whole philosophy here. Think of transposed convolution, very basically, as learning to zoom in intelligently, not just stretching pixels, but learning to create relevant high-res details.
So it's learning to fill in the gaps, essentially, but in a smart way for understanding. Got it. What's innovation number two?
Number two is the visual prompt injection strategy.
Visual prompts, like clicking on something or drawing a box. How does Pixel Sale handle those differently? What's the innovation there?
Well, the challenge is, how does this single transformer, which starts by seeing the image as a bunch of low-level patches, how does it understand a high-level prompt, like a box or a point? Normally, you might have a whole separate encoder just for those prompts.
Right.
Pixel Sale does something pretty clever. They map these visual prompts, points, boxes, even masks. They map them into special text tokens.
Wait, text tokens for visual things.
Yeah, it's a neat idea. These special tokens get added to the language model's vocabulary. So when you give it a visual prompt, say a bounding box, the model gets the corresponding text token injected right alongside the image patch tokens early on.
Ah, so it fuses the prompt information with the visual data very early, all inside the one transformer.
Exactly. And crucially, this avoids needing that extra visual prompt encoder. Again, sticking to the simplicity principle.
It's like giving the language part of the model special words that mean, look at this specific spot. That is quite elegant. Okay, and the third big innovation.
The third piece is the vision expert distillation. strategy.
Distillation. Transferring knowledge from a teacher model to a student. We hear about that a lot. How are they using it here? What's novel?
So the goal is to boost Pixel Sales' ability to pull out fine-grained details and just generally improve the quality of the segmentation masks it generates.
Without massive segmentation training datasets.
Right. Training on those huge data sets can be expensive and maybe even hurt the model's ability to follow general instructions. So instead, they use distillation. What's neat is how they do it. They borrow expertise from established models, they take mask features from mask2formers decoder
Okay.
and apply that to Pixel Sales' upsampled features. And they also take features from SAM2's encoder and apply that to Pixel Sales' low-resolution features. It's like getting guidance from different experts at different stages.
So they're kind of cherry useful bits from these powerful segmentation models and using them to teach the simpler pixel sale.
That's the idea. And the paper emphasizes this gives them much better segmentation, but with only a negligible increase in training time. So it's efficient knowledge transfer.
Okay, these three innovations, upsampling, prompt injection, distillation together, they paint this picture of a really streamlined system, very focused. Now, how do you test something like this? Especially if existing tests aren't quite capturing the nuance, that's where PerBench comes in, right?
Exactly. The researchers felt that the existing benchmarks for pixel-wise MLLMs had some gaps.
Like what?
Well, they argued they often lacked really detailed object descriptions, didn't rigorously test how well models understood different types of visual prompts, and didn't properly evaluate tasks where you need to use both visual prompts and text together to find something.
Right, combining modalities. So PerBench was built to be tougher, more nuanced. What are its standout features, the innovative parts?
It has three main innovative aspects. First, detailed object descriptions. These aren't just short labels. They used advanced MLLMs to generate rich, descriptive captions for objects, and then humans carefully checked and refined them. Much more detailed than usual.
Okay, deeper descriptions to test deep understanding. Makes sense. What else?
Second, they changed how they test visual prompt understanding. Instead of just asking the model to describe the prompted area, they framed it as visual prompt-based question answering, multi-choice.
Ah, like MME or MMBetch.
Inspired by those, yes. It forces the model to make a specific choice based on the prompt, which they argue is a more direct and quantifiable way to see if it really understands the prompt, not just generates plausible text.
Yeah, multiple choice is harder to bluff. Okay, and the third feature?
The third innovation is a completely new task, visual text referring segmentation, or VTRS.
Visual text referring segmentation.
Yeah, so here the model has to present an object that's pointed out both by a visual prompt, like a click, and by some descriptive text.
So it can't just rely on the click or just the words. It needs both.
Precisely. It has to integrate both sources of information to find and segment the right thing. It's a tougher, more realistic test of that joint understanding.
That does sound challenging. So PerBench is designed to really push these models.
Yeah, the researchers explicitly say it reveals the limitation of current state-of-the-art models on these fine-grained and mixed referring tasks. It sets a higher bar.
Okay, so they built this tougher benchmark. How did Pixel Sale actually do? Especially compared to those bigger, more complex models. What did the results show academically?
The results were pretty striking, actually. On the standard referring segmentation benchmarks, RefCogs plus B, RefCogCog, the usual suspects Pixel Sale did really well. Both the 0.5 billion and 3 billion parameter versions were purposeful and often better than much larger models like GGLAM 7B, OMG LA 7B, SA2VA 4B.
Better. Even though they're simpler and smaller.
Yes, particularly on the harder datasets like RefCog Plus and RefCog, they reported outperforming them. It really highlights that simpler pipeline.
Wow, okay, that's compelling evidence for their approach. What about understanding the visual prompts specifically?
On the zero-shot region captioning task on RefCog, which tests that prompt understanding again, Pixel Sale was strong. The 3B model beat the larger models like OMG Alava and GLAM on the meter score, which measures caption quality.
And on their own benchmark, PerBench, the really challenging one.
On PerBench, the Pixel Sale 3B model came out on top. It got the highest overall score, beating models like GGLAM and SA2VA across all three tasks, the detailed captioning, the visual prompt multiple choice questions, and that tricky VTRS task.
A clean sweep on the new benchmark. That strongly suggests its design choices really pay off for these specific challenges. Did they look at general VQA benchmarks too?
They did. The picture there was a bit more mixed. At the smaller 5B scale, Pixel Sale showed improvements over its base model. But at the larger 3B scales, it was more on par with the base MLLMs.
Why might that be?
They suggest it might be down to the training data they used. Perhaps the co-training dataset wasn't large or diverse enough, especially regarding segmentation and visual prompts, to push performance further on those very general VQA tasks at larger scales.
Right. Data is always key. Now, to be sure that each of their innovations was actually doing something useful, they must have done ablation studies, right? Picking apart the model.
Oh, absolutely. Standard practice, and crucial here, the ablations confirm that yes, each of the three main components, the upsampling module, the visual prompt injection, and the distillation, each one significantly boosted performance.
So no single silver bullet, but all three parts were pulling their weight.
Exactly. They specifically noted that the visual prompt injection really helped with understanding prompts, obviously, but it also had a positive knock-on effect for the referring segmentation tasks.
Interesting synergy there.
Yeah, and as you'd expect, scaling up the base model size and the training data also helped. The studies also confirmed the distillation from Mask-2 Former and SAM-2 improved mask quality efficiently without much extra training time, validated that whole strategy.
Did they get any visual sense of why it was working better, like looking inside the model?
They did some visualization analysis, yeah. It suggested Pixel Sail learns denser or varied features for both the image and the masks compared to a baseline without these innovations. The segmentation edges looked sharper too.
Okay.
And interestingly, it seemed like the image features focused more on high-level concepts, like what object is this, while the mask features were more about the perception side, where exactly is this specific instance, a bit of specialization going on.
Fascinating. So even with this success, what what do the researchers themselves see as the next steps, thinking about the academic path forward?
The main limitation they point to is the size of the data set they co-trained on about 1.7 million samples. It's decent, but maybe not large enough to unlock everything.
So more data needed.
That's the big future direction they highlight. They're optimistic about exploring pixel sale with much, much larger data sets. Like the SA1B dataset has billions of masks and prompts.
Billions. Wow.
Yeah. They think scaling up the data like that could really push pixel sales capabilities even further and perhaps overcome those plateaus seen on some general V2A benchmarks.
So they've built this efficient, simpler engine, and now the idea is to fuel it with massive amounts of data to see how far it can go.
That seems to be the plan. They've shown the potential of the architecture and the innovations. Now it's about scaling the training.
Okay, so for you, the learner listening to this, the big takeaway seems to be that Pixel Sale is offering a really different way to think about AI understanding images at the pixel level. It's showing that maybe we don't always need more complexity. Sometimes a simpler, unified design with smart, targeted innovations can be just as good or even better.
Absolutely. That's the academic contribution right there. A novel encoder-free setup, those specific innovations in upsampling, prompt handling, distillation, plus the new benchmark, PerBench, to measure progress more accurately. It's a significant package.
It really makes you wonder, doesn't it? Could this focus on architectural simplicity be a path forward, not just here, but in other complex AI areas too? Could it lead to systems that are maybe more efficient, more accessible, but still deeply capable? And if this for understanding, what other AI challengers might benefit from rethinking the architecture and adding just a few really clever enhancements? Definitely something fun. Worth checking out their project page if you're curious, and maybe keeping an eye out for code. Thanks for joining us for this deep dive.